Okay, so sometimes it's easier to think of composite functions that we're going to apply the chain rule to as being composed of an inside and outside function. I think one of the hardest things about the chain rule is not necessarily doing it, but recognizing what are the two parts that make up this composed function. Sometimes it's obvious, but other times it's not so obvious. But it can be easier if you think of an inside and an outside function. So from our last example, we had this equation y equals brackets 4x squared minus 1, and then that quantity squared. And what we did was we thought about we're looking for pieces of this composite function that are easy to differentiate. And we said here that 4x squared minus 1, well, that's a polynomial. We can differentiate that easily. And if we call this u, if we replace it, now we're replacing it to make things easier. Think of u. Think of u as a middleman, like a go-between x and y. Think of u as a middleman. So if we call 4x squared minus 1 u, we can call that our inside function, right? G of x becomes this polynomial function, which we know how to differentiate, 4x minus 1, which is equal to u, by the way. And then the outside function is going to be now a function of u after we replace it. So y, which is, f of, so we've replaced this now with u, so it's a function of u, and we just have u squared, the power of 2. So now we've decomposed it using u as our middleman. Now, we can work out the chain rule either in Leibniz notation or function notation. Now, Leibniz is the notation where we use y and dy, dx, and so forth. So let's start with the Leibniz notation. So if we have y equals our function, right, 4x squared minus 1 squared. Well, then we defined u to be 4x squared minus 1, our inside function. And therefore, after we substitute this u, y really becomes u squared. Yeah. And now, remembering our kind of rule, the chain rule in Leibniz form, we said that dy dx was equal to dy du times du dx. So again, when we take our derivative of y with respect to u, we're looking at this equation here, and we get, we know that dy du is simply 2u, and then dy dx, or du dx, coming from this top equation, we know that du dx is equal to 8x, taking the derivative of 4x squared minus 1. And so we see that our derivative dy dx is equal to the product of those, 2u times 8x, which was, and then after we replace u, again, this was 2 times our u, 4x squared minus 1 times 8x. And we could expand this, but we don't have to at this point. But in function notation, it works a little bit differently. We said that f of x is equal to, again, 4x squared minus 1 squared. And we were looking for that inner function. Oh, no, sorry. We would, not f of x. We want to consider this as a composite function. So we want to think of it as a composed function of two functions, f and g. So it should look like this. And again, our inner function, our inside function, is going to be g of x, which we're going to call just 4x squared minus 1. And remember, we can still call this equal to u. That's our middleman still. And now we can redefine, we can say that the whole thing is f of u, because u is the same as g of x, is going to be equal to, instead of 4x squared minus 1, we're just going to call it u squared. And so now our rule, our derivative, this is the derivative operator, d dx of the composite function, f of g of x, is going to be equal to the derivative of f with g of x inside times the derivative of g with respect to x. And we'll see that this is going to be equal to, we first need to find the derivative of f. So if we look at this, we know that f dash of u is going to be 2u, and we know that g dash of x is going to be 8x. And so now we know that we're going to plug, instead of u, right, this is our f dash of u is 2u, but instead of u, we're going to place g of x. So this is going to become 2 times g of x, which is 4x squared minus 1. And then we're going to multiply just by the derivative of g dash x, which we saw was 8x. And you can see that we arrive at exactly the same answer. It's just a matter of notation. So you may want to think about highlighting in Leibniz form. Really, we're interested. This is the chain rule in Leibniz form. But in function form, this is what it is. And some people prefer to use one or the other, and I don't personally care which one you use, but you do need to be aware that depending on the form that the question is asked in, you probably need to be prepared to use both notations. And we have in your notes summarized down here in this box the derivatives. So a little bit more about the chain rule with different notations here.